The project aims to use a behavioral cloning approach to train a convolutional neural network to drive a car autonomously in an indoor circuit and evaluate its generalization skills to unseen lighting conditions.
Ready?
A driving policy is recorded in images labeled with throttle and steering angle values. The vehicle is equipped with a Raspberry Pi, and a single RGB camera is the only sensor used to train the neural network. An expert drives the car in 2 different sessions, collecting images and labels at a rate of 20 images per second. 2 different training approaches are used to train 4 different models. Then each of the 4 models is tested and evaluated under 4 different sets of conditions, including lower lights, higher lights, lower lights under adversarial attack and higher lights under adversarial attack. It is essential to notice that all the dataset used to train the models was strictly collected under low lights conditions. Therefore, it is possible to evaluate the model's generalization skills to the unseen conditions and measure the results from the 2 different training methods. The first model tested was trained using the smaller dataset and a standard training method. The model performed well in low light conditions. However, it seems to be overfitting and failed to generalize to all the other conditions, colliding 5 times when exposed to the unseen higher lighting levels. The model learned to drive well under low lights conditions and had a good performance, with no collisions in 2 laps. This was expected as this was the condition in which the dataset used for training was collected. However, when the input images are disturbed with an adversarial attack, the model fails, colliding multiple times. A perturbation is added to all the images captured by the camera under an adversarial attack. Thus, predictions are expected to fail as the model was trained without adversarial examples. Having to deal with unseen adversarial examples, the model fails to generalize and struggles to drive, requiring multiple human interventions and colliding 12 times in 2 laps. The first model was exposed to the following condition with higher light levels. The overall luminance levels in the circuit are increased, and the model fails to generalize to unforeseen lighting levels, overfitting to the lower light training conditions. The model created using a standard training method was unable to generalize to higher lights and collided 5 times in 2 laps. The model trained with a small dataset and standard methods was exposed to the last condition. The unseen higher lights levels are maintained, and an adversarial perturbation is added to the input images that the model has to make predictions on. The model fails to predict clear steering and collides 7 times in 2 laps. The next model uses a more sophisticated training method in which adversarial images are generated and mixed with the regular images. The results show that the model created with the adversarial defense method was more skilled in generalizing unseen conditions. It maintained the baseline performance with no crashes in low lights and registered no collisions in unseen higher light levels. The model trained with adversarial defense methods could maintain the same accurate driving with no collisions in 2 when driving in lower lights. The model showed a significant improvement in generalizing to the adversarial images, despite colliding 2 times during 2 laps when attacked and in lower lights. The performance was superior to the model that used a standard training method with the same dataset. The model trained with an adversarial method could generalize and steer clear of collisions for 2 laps, despite being exposed to unseen higher light levels conditions. When exposed to the adversarial attack and higher lights, the model trained with the adversarial method slightly improves compared to the models trained with standard methods, reducing the number of collisions to 5 in 2 laps. The collisions could be justified by training the model with a mix of standard and adversarial images. In contrast, all images that the model is trying to predict have perturbations added during the attack. A new autopilot model was created using standard training methods. However, a larger dataset with double the data was used to train the model. The results suggest a discrete improvement in the overall performance, maintaining the baseline of no collisions in lower lights. Like the previous model, when exposed to the same low lights conditions in which the model had been trained, it drives the circuit precisely and completes 2 laps without collisions. In the following condition, when adversarial examples are added to the input images captured by the camera, the model fails to generalize to the unseen images and collides 10 times in 2 laps, showing only a minor improvement in comparison to the previous model, considering the larger dataset. The model was tested in higher lights levels. Again, the larger set of data only contributed to a mild improvement compared to the previous model, colliding 4 times in 2 laps. Both models tend to collide in similar locations, coinciding where the recorded lights level was higher in the circuit. The model did not perform well in higher lights levels and with adversarial attack added on top of all the input images. these conditions are entirely new to the model, and increasing the training dataset made the model overfit the training data even more, colliding 9 times in 2 laps. Using standard training methods with a larger dataset was not enough to create a robust model capable of generalizing to unseen light levels. Like the previous model, it overfits the training conditions and fails to make accurate predictions in unseen higher light levels. The last model tested in the experiment was trained using an adversarial defense method in which a batch of adversarial images is added to the larger dataset. Its generalization skills are superior to the models trained with standard methods. It registered no collisions in both lower lights and the unseen higher lights and fewer collisions when under adversarial attack. Increasing the dataset used to train the model with adversarial defense methods did not affect the performance in lower light levels, maintaining the baseline of no collisions in 2 laps. However, increasing the size of the dataset did not yield a significant performance improvement. It registered 3 collisions and several human interventions in 2 laps, demonstrating that an increase of data could lead to the model overfitting even more to the training conditions. The model trained using an adversarial method drove accurately and registered no collisions in 2 laps in unseen higher light levels. It shows the consistency of using adversarial defense methods to make models more skilled and capable of generalizing to unseen conditions. Increasing the amount of training data did not increase the model's performance. Although registering lesser collisions than the models trained with standard methods, under adversarial attack, the model had the same amount of collisions as the model trained with a smaller dataset. Overall, using adversarial defense methods has increased the model's generalization skills to unseen conditions, as in unseen higher light levels, the model trained with adversarial images reduced the number of collisions from 5 to 0. On the other hand, using a larger set of data for training the models did not exhibit significant improvement in the performance.